6.3 Exponential Functions. So, Malthusian catastrophe. So, this is a economics person back in like the late 1700s who came up with this. So, Robert Malthus, that's his name, states that the growth of human population is governed by the rate of crop production. Because that's true. Our population, the more food we have, we can populate. The less food we have, we die. In the future, if the growth rate of crops decreases, then human population growth is decreased, and there might come a day when we may have extremely limited supply of food, which can cause widespread hunger and starvation. So exponential functions is a reminder of how efficiently do we utilize the available resources. So let me give you some examples of exponential functions, stuff that we might have already seen before, and it's super important. If you took US history, if you're from here and you took US history, you know this. You see the world population and the growth rate. It's fine. We grow nice and linear. We're nice and slow. We grow nice and neat and everything is fine. And then right here, boom. Yep, that's the baby boomers because of World War II. So World War II is actually what led us to advance. Not only that, but it's not only the World War II and the people, the baby boomers, but technology advanced so fast during World War II. A lot of things were invented. So after that, everything is exponential. Technology, how we grow as a society, all of that is going to be exponential because we had a real big shift in our history. So this is a graph of unbound growth requires accelerating cycles of innovation to avoid collapse. So I'm going to read the white text underneath. I'm kind of explaining this graph, but it's actually from a TED Talk. It's super interesting. You can just look up TED Talks, The Surprising Math of Cities and Corporations. It's 17 minutes long, but it's actually very fascinating on how wherever you are, it has a certain growth rate to it or a certain happiness rate to it. It's actually very fascinating. It blew my mind when I was researching things about exponential functions, and very, very enjoyable watch. Watch it one morning when you're doing nothing. So this quote from this video, there is a continuous cycle of innovation that is necessary in order to sustain and avoid collapse. The catch, however, to this is that you have to innovate faster and faster. So the image is that we're not only on a treadmill that's going faster and faster, but we have to change the treadmill faster and faster. We have to accelerate on a continuous basis. So basically is we're growing so fast that if we don't change things, we'll collapse. You know when you have your markers and you put them together like a sword or a lightsaber, and you just build and build and build, and then out of nowhere they just collapse over onto the floor because it's too much. That's exactly like this. That's a perfect metaphor for what we're doing. So unless we change, we're not going to fix the things that we're making errors as humans. But the catch is that we every time we change, we have to change faster, we have to change faster, we have to change faster, 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 faster. There's going to be less wiggle room for advancement. And that's where we're at right now. We need to change 10 years ago in order to solve a lot of issues that we're having now with food and agriculture and climate change. So that's the image, is that we're on a treadmill that just keeps going faster and faster and faster and faster, and we just need to keep running faster and faster and faster. That's why engineering and being able to critical think and thinking outside of the box is really going to save us as a humanity, because we have to keep changing, keep changing, keep changing. Agricultural engineering is one of the most important degrees right now, because that is going to literally mean how long are we living or not. So that was my catcher. I wanted to catch you into why do we talk about exponential functions? Well, they kind of revolve around our lives. Not only that, but they revolve around so many other things that we're going to get into in the later parts of chapter 6. Just as a reminder, because man, it could be a hot minute since you've seen rules or laws of exponents. So laws of exponents, you have all real numbers, a and b are greater than 0. So if you have a dot in between, you add exponents. If you're multiplying your bases, you add your exponents. If you have parentheses, you multiply your exponents. If you have two terms and an exponent on the side, it goes to both. 1 to the power of anything is always going to be 1. This is something that we talked about earlier in the semester. Negative exponents are just fractions. And since it's 1 over, we can also throw it on the outside because it doesn't change if you distribute it to both. It's still 1 to the power of s is still 1. A to the power of s is still a to the power of s. And remember, anything to the power of 0 is 1. It's not 0, it's 1. So anything to the power of 0 is always going to equal 1. Let's talk about what an exponential function looks like in its purest form. So an exponential function is f of x equals c times a to the power of x. A is a positive real number, so a has to be greater than 0. It's not going to be 1. C cannot be 0. It's a real number. The domain is all real numbers, so that's important because remember, domain is what x can and cannot be. So if we're talking about exponential functions, x can be anything you want it to be. The base, a, that's called the growth factor, the growth rate, another term for that. F of 0 is when c times a to the power of 0, that's just c, because anything to the power of 0 is just 1. That's called our initial value. So if you want to find your initial value, you make x equal 0, because that's what you started with. X can mean time. It can mean a whole bunch of other things. You'll see later on in chapter 6 how that x, it really does mean time when we use that in its context of time. We're going to identify linear or exponential functions. So we're going to determine if we have a linear, exponential, or neither. If it is linear, we're going to find the linear function. If it's exponential, we're going to find the exponential function. If it's neither, we're just not going to do anything. So remember, linear is all plus and minus. That's linear. Linear, we add so many. We go up and right, or whatever. Exponential, it's the other ones. Exponential is multiplication and division. So that's what we're going to look for our average rate of change. Our average rate of change for linear is always going to be plus and minus, and it's going to be constant. For exponential, it'll always be multiplication or division, and it's still going to be constant. It'll just either be multiplication or division. So let's look at A. We have -1, 0, 1, 2, 3. That works out. Honestly, your x's are going to work out for this. Really, we want to pay attention to our y's. So for our y's, let's see if we can add, subtract, multiply, or divide. So 5 to 2, I can't divide to that. I can't multiply to that. All I can do is subtract. So from 5 to 2, we can subtract -3. Okay, let's see if that's consistent all the way down. 2 to -1, that's another -3. 1 to -4, that's another -3. -4 to -7, that's another -3. Because they are all -3 and it's consistent all the way down, we know that this is linear. Because we know this is linear and we need to write a function, we know that's going to be f of x equals mx plus b. So that average rate of change, remember, that's your m. So we'll have -3x plus b. Remember, b is your y-intercept. So b is always going to be 0 number. You will be given it. So let's look for 0 number. We do have 0 number right here. It's 0, 2. So that means our y-intercept is plus 2. And there is our linear function. Go back to 2.3 if you're a little weary on f of x equals mx plus b. Alright, b, we have -1, 0, 1, 2, 3. Okay, those all work. Really look at your y's. So 32 to 16. First, we want to see if we can multiply or divide, then add or subtract. So 32 to 16, we can actually divide by 2. 32 to 16, we can divide by 2. 16 to 8, that's another divide by 2. 8 to 4, that's another divide by 2. 4 to 2, that's another divide by 2. So since it's being divided by 2, we know for sure that's exponential. However, exponential is never division. if we look at our exponential function for itself, it's all multiplication. It's c times a to the power of x. So instead of dividing by 2 actually just means multiplying by 1/2. I'll give you an example. I'm going to erase it so you don't actually have to write this. So if I said 4 divided by 2, we know that's 2. I can also do 4 divided by 2. It's the same thing as 2. Remember, division is just a fraction symbol. So we know that we're actually halving every time. So 32 to 16, that's half. 16 to 8, that's half. 8 to 4, that's half. 4 to 2, that's half. So that's actually your growth rate. You're taking half off every single time. And we just learned that growth rate actually stands for a letter, a variable. It stands for A. A is our growth rate. So that actually gives us our A. So when we do an exponential function, the parent function is f of x equals c times a to the power of x. When we're writing an exponential function, we're not caring about c. We're just putting in our growth rate. So we have f of x equals our a, which is 1/2, all to the power of x. I want you to go ahead and pause and do C. Alright, I hope you did. Let's do it together now. So our x's are negative 1, 0, 1, 2, 3. Okay, we're good there. Again, I'm telling you that it's okay. Just look at your y's for this, because that's what we're really looking for this example. Let's look for our y's. So first we want to see if we can multiply or divide. So 2 to 4, we can actually go times 2. Okay, that works. However, if we do 4 to 7, that's no longer times 2. That's not, 4 to 7, I can't multiply that. So it's no longer exponential because I can't keep going. Also, 7 to 11, that's not times 2. 11 to 16, that's not times 2. So we know for sure that this is not exponential. Let's see if we can add and subtract. So let's see if this is linear. So 2 to 4, that's plus 2. 4 to 7, that's plus 3. It already changed. Your average rate of change needs to be consistent plus or minus. It's no longer consistent plus or minus, so it's neither. Let's graph. So as always, we're graphing. We gotta practice graphing exponential functions, so let's graph the exponential function f of x equals 2 to the power of x. Alright, as always, just like in piecewise defined functions, if we don't know how to graph something, guess what? We bust out a t-chart. I know it seems silly, but that's just how we do it in higher level math. Interval charts are just fancy t-charts. Remember, the domain for every exponential function is all real numbers. Since we know that, x can be anything we want. So what numbers do I pick? I usually pick -1, 0, and 1. Why? Well, exponential functions are really big. So I want to pick smaller numbers. I want a negative and I want a positive. And like I said with piecewise defined functions, if you can pick 0, you should probably pick 0 because it's an intercept. So let's plug it in. We have y equals 2 to the power of -1. Remember, negative exponents are not allowed, so we actually have to flip it. So that means we'll have 1 over 2. We just flip it. There's no other exponent. It's just 1 over 2. So 1/2. Let's do the same thing. We have y equals 2 to the power of 0. Remember, anything to the power of 0 is 1. And then we have y equals 2 to the power of 1, which we know is just 2. So we have negative 1, 1 half, 0, 1, and 1, 2. So when I create my coordinate plane, I'm only going to go to 2 because that's all we have. Let's plot our points. We have negative 1, 1 half. We have 0, 1. And we have 1, 2. Now I'm going to connect these dots, and you're going to see I'm not going to cross a line here. So I'm going to connect my dots. I'm not going to cross the x-axis, and I'll tell you why in a second. So we don't cross the x-axis here. Now, why? Why don't we cross the x-axis? Well, the reason why is because there's something called a horizontal asymptote. We're going to learn way more about those in Chapter 5. So our horizontal asymptote is y equals 0. How do we get y equals 0? There's nothing here. You're right, there's nothing there. Nothing in math means 0. So whatever constant you have on the outside, that's your horizontal asymptote. Also, do you notice that this is negative 1 half? You can plug in any number for x and it will never be a negative y. And I mean that. Let me show you. So let's say we plugged in y equals 2 to the power of, let's say, negative 100. That's just going to be 1 over 2 to the power of 100. That's just a really, really, really tiny decimal. It's just going to forever, ever, and ever approach this asymptote. It's just going to approach it forever and ever and ever. So this is a graph of 2 to the power of x on Desmos. It's just to show you a real calculated graph because anything we do by hand, you know, is a sketch. So this is done perfect. So if we look and keep zooming, and I mean it, we can keep zooming. You see how it never crosses the x-axis? Ever. Ever. It's going to forever and ever and ever and ever and ever approach. There is a separate video on the modules on how to graph with my math lab. I am going to verbally go over it with you, but if you really want to see it with my math lab up on the screen, I have a separate video for that in the modules right below where you click this one. So when you're graphing exponential functions, the first thing you're going to do is click the graph tool, and then you're going to plot a point either at 0, 1 or 0, 0. It doesn't matter. You can plot the point at 0, 1 or you can plot it at 0, 0. That's okay. It's totally up to you where you want to plot the first point. Both are going to be fine when you use my math lab. So you plot the point, and then from there, a little box is going to come up. To plot the point, you hit exponential tool. And after that, this little box is going to show up right at the bottom, this little box right here. So when you click exponential tool and plot the point, from there you need to do your transformations. So make sure your base matches your base. We have a base of 3. We have a base of 3. So make sure that these bases match. And they do, okay? Now move on. We have regular x, that's okay. And then we have a minus 4. So minus 4, that's the asymptote. The constant that's not attached to the variable, just the normal number, that's your asymptote. So our asymptote means we need to shift vertically down 4 because it's minus 4. So when we do our vertical shift, we want to go to minus 4. And here, that's going to be our asymptote. It's never going to cross minus 4. If you want a detailed explanation and actually seeing it on my math lab, just watch that video. Now we're going to learn to solve exponential functions. So if a to the power of u equals a to the power of v, then u equals v. This is saying if you have the same bases, you're allowed to cancel them out because they're common factors. So really what we want to do to solve exponential functions is to get the same base, get the same big number. Usually you're going to use one of 3 numbers. I'll explain that when we get through part A. So we have 3 to the power of x plus 1 equals 81. 3 is prime. I cannot change that whatsoever. 3 is just a regular number that I can't simplify, I can't change, I can't make it look different at all. So that's it. It's just 3. So 3 to the power of x plus 1. Now, since we have a base of 3, We want to see, can we make 81 have a base of 3? Meaning 3 squared, that's 9, so that doesn't work out. 3 cubed, that's 27. That doesn't work out. 3 to the 4th, guess what? That's 81. So 3 to the 4th is actually the same thing as 81. I don't know if you remember back in the beginning when I said you can do anything you want in math, make it work for you. But it has to make sense, it has to be fair. It makes sense because that's the rule that we have to have the same bases. We have to have the same big numbers in order to have a common factor. So we can get rid of them and just bring down the exponents. So we get rid of them, we bring down the exponents. So now we have x plus 1 equals 4. We subtract 1, and then we get x equals 3. So our solution is 3. And rewrite it as a set because sometimes you can have more than one number. All right, part B. We have 4 to the power of 2x minus 1 equals 8 to the power of x plus 3. So we need these numbers to be the same. That's our goal, is for these numbers to be the same. So 4, okay, that's a nice number, but I can simplify 4, so let's just keep that in our minds. 8, well, let's see if I can have a base of 4 be 8. So 4 to the power of 1, well, we know that's 4. 4 squared is not 8. 4 squared is 16. So I cannot use base of 4. It doesn't work. We always have to make sure it's going to equal what the base is actually given. So 4 is not going to work. Let's try using 2. Let's try using 2. So 2 to the power of 1, we know that's 2. 2 squared, oh, that's 4. So 2 squared is actually 4. So 2 squared. However, on the top, we still have 2x minus 1. So we just rewrite it. So we changed the 4 to be 2 squared, because 2 squared technically still is 4. We're just changing it to make it work for us. Now let's try 8. So 2, 1, we know that's 2. 2 squared, we know that's 4. 2 cubed, oh, there we go. 2 cubed is actually 8. So we can switch 8 to be 2 cubed. But don't forget, we also have this x plus 3 on top, so we just keep writing it on top. So 4 became 2 squared, 8 became 2 cubed. We can get rid of our bases now, because those are common factors. So we're left with 2 parentheses 2x minus 1 equals 3 parentheses x plus 3. Let's solve for x. We're going to distribute, so we got 4x minus 2 equals 3x plus 9. We're going to subtract 3x to get x together. So now we have x minus 2 equals 9. Add 2 to get x by itself. And we get x equals 11. Now, since the domain is all real numbers, once you get an x, you're good. Just keep moving on. So there's bases we want to usually use. Now I say usually because sometimes, things happen. You have big numbers. So the bases you usually want to use are the numbers like 2, 3, and 4. Rarely are you going to use 5, 6, and so on. Because remember, 5 squared is 25, 5 cubed. I mean, we're talking about really big numbers here. That's why our bases need to be small. We always want to go down in base. You never, ever, ever go up in base. It's like when you find the LCD. So we always want to go smaller, not bigger when we find our bases. And usually the numbers you're going to use are 2, 3, or 4. Sometimes 5 or 6. It happens sometimes you have to use a base of 5, 6. But you really want to try sticking with 2, 3, 4. Okay, E. E is something we're going to be using in this class, not in just too much detail, but we are going to use it. So E is kind of like pi. Pi is 3.141579, so on. E is actually 2.71828. E can be found on your TI-84 by pressing the second key, then the divide key. That's all you need to know about E, is just that we're just going to use it. All right, let's solve. We have e to the power of negative x squared equals e to the power of x all to the power of 2 times 1 over e cubed. So we're trying to solve exponents. How do I know? We have variables as exponents. So in order to solve exponents, we need the same base. First, let's clean this up. Exponents don't have fractions. Exponents should just all be exponents. So I want to change this to no longer be a fraction because we can. We're allowed to. We know that 1 over a is a to the power of negative 1. We know a negative exponent is just a fraction. So let's change that up and just clean things up when we can. So you have e to the power of negative x squared equals, let's go ahead and distribute because that's the rules, the laws of exponents. We can distribute this to make it e to the power of x times 2, that's 2x. All times, let's go ahead and switch this to e to the power of negative 3. Our goal is to get the same base. Look it, we have the same base now. Didn't really have to do much work, we just had to use the laws of exponents. Now that we have the same base, those are common factors, so we can take them out. What we're left with is negative x squared equals 2x minus 3. Because that's negative x squared, we just bring it straight down. 2x, we bring it straight down. Minus 3, we bring it straight down. This is a quadratic, so since it's a quadratic, we need to equal it to 0. So we have 0 equals x squared plus 2x minus 3. Because this is a quadratic, we need to factor. So we can factor this into x plus 3, x minus 1. We set each factor equal to 0. We get minus 3 equals x and 1 equals x. So we have two solutions. That's why we use a solution set. We have a solution of negative 1 and 3. Both will work because the rule, the domain, is all real numbers. Also, another reason why we have two answers, because it's squared. Squared means at most you'll have two answers. Alright, I want you to just try. Even if it takes you 5 minutes, I just want you to try example 6. Again, no one's going to know, only you. I am hoping you're trying these things. That's the only way you're going to learn, is sometimes you're going to get stuff wrong, and that's okay. We make mistakes. It's to, how do we learn from that mistake? How do we figure out, okay, this is the mistake I made. How do I correct it, right? So it's okay to make mistakes. It's okay to mess up sometimes. You're always going to mess up in life, and it's okay. It's just how do we react to how we mess up. So hopefully you tried it. All right, our goal is to get the same base. It's 3. If it's already prime, like 1, 2, or 3, you don't touch it. Because 1, 2, and 3, those are prime numbers. You can't do anything with that. So we just keep it as 3. Now we have to see, can we make 9 be a base of 3? Well, let's see. Well, 3 to the power of 1, that's 3. 3 squared, that's 9. So 9 is actually 3 squared. But don't forget, we also have the 5x on top. Now that they have the same bases, those are common factors, we can get rid of them, and let's just bring everything down. We have x squared minus 56 equals 2 times 5x. Let's multiply. So we have x squared minus 56 equals 10x. This is a quadratic, so it should equal 0. When we do, we have x squared minus 10x minus 56 equals 0. Because this is a quadratic, we need to factor. When we factor this, we can factor it into x minus 14 and x plus 4. We set each equal to 0, so we have x minus 14 equals 0, x plus 4 equals 0. So we're left with x equals 14 and x equals negative 4. So our solution set is negative 4 and 14. You notice that at the beginning it was squared. So at most, you could have two answers. Example 7, you need to use a TI-84 or your Casio calculator. I don't know how to use a Casio calculator, so you're going to have to find out on your own. per the orientation module I stated, I only use the TI-84 to do examples. You could go to the Math Center and get help. You can go to tutoring online and get help to use any other calculator. However, it needs to be a graphing calculator. So what if you don't have one? You need to rent one and do your test with a rented calculator, or if you have a PC, you are allowed to use the Wabbit 2, however you want to say it. If you go to the orientation module, you can use that calculator that I have listed. So between 9 p.m. and 10 p.m., cars at Jack in the Box's drive-thru at the rate of 12 cars per hour, that's 0.2 cars per minute. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 p.m. There is a typo on your sheet. It should be 25, so it should read f of t equals 1 minus e to the power of negative 0.25t. So make sure it's 25t. Let's determine the probability that a car will arrive within 5 minutes of 9 p.m., that is, before 9:05 p.m. Then we're going to determine the probability that a car will arrive within 30 minutes of 9 p.m., so before 9:30 p.m. We're going to graph it, that's when we need our calculator, and then we'll do some other parts. So, you know those little strips, those little like cords you drive over sometimes on the road? Like they look like literal extension cords taped to the ground? So they're actually determining how many cars pass by at each time. They're determining the probability that a car will come through at this time or this time or this time. So then that's how they determine how do they do construction, and if they need to do construction, or they need to add more lanes and light cycles and all of that stuff. So that's actually how city planners and civil engineers do all of this. They use those little extension cord things that go on the ground, and they're just calculating how many cars drive past at each given time. So let's determine the probability that the car will arrive within 5 minutes. So 5 minutes. Minutes is time. Time is a variable, t. Remember how I told you t, lowercase t, is always time. That will not change. So we're actually given t of 5. Let's just plug it in. So we have f equals 1 minus e to the power of negative 0.25t. In this case, t is 5. You're going to need your calculator for parts C, D, and E, a graphing calculator, a basic calculator for A and B. So with our calculator, we're going to plug this in. We have 1 minus e. E is second divide to the power of negative. So negative is on the bottom. Negative and minus are two different things. Negative 0.25 parentheses 5. And we get 0.7134952031. So let's write that. Let's record that answer. So we have 0.71349 so on chance. That means there's a 71% chance. Now, what does that actually mean for this word problem? So what this means is there's a 71% chance that a car will come through the drive-thru between 9 p.m. and 9:05 p.m. So that's what we found using this statistical model. If you go to statistics, you'll come up with the model from data given. But using statistics, we were able to come up with, hey, with what they're given, within 9 and 9:05, there's a 71% chance you're going to get a car through the drive-thru. Let's do part B. So part B, we want to know, determine the probability that a car will arrive within 30 minutes of 9 p.m. So we're saying 30 minutes. Minutes is time. So we're actually given 30 for our t. Let's plug it in. We have f equals 1 minus e to the power of negative 0.25 times t. In this case, t is 30. Let's use our calculator again. So if you're using a TI-84 or an 83, you can just use your arrow, scroll up, hit enter. The only thing that's different is 30. Instead of 5, we want 30. So guess what? Just type in 30. And hit enter. Or you can just type it out all over again. I already showed you in part A. So there's a 994469156 chance. That's a 99% chance. Let's go ahead and write that. So there is a 99% chance that a car will come through the drive-thru between 9 p.m. and 9:30. It can never be 100%. Why don't we round up to 100? Because you can't. That's never 100%. You cannot determine that based off of a car. Only 100% thing you can do is like rolling a die or something that there's no variability to it. So a drive-through question or anything happening like weather, 99 is as high as you can get. It can never be 100% because we don't know. It's just like in Florida where it'll say 20% chance of rain and it'll rain, or it'll say 90% chance of rain and it won't rain because there's still a certain period or a chance that it won't rain. Part C and E we need our calculator for. Part D is just something to explain. So we are going to need a graphing calculator for part C and E. Part C. Let's graph. So in order to graph anything with your calculator, you're going to hit y equals. So after you hit y equals, make sure there's nothing in here. Press down, go back up, make sure there's nothing in here. And I mean it, like press all the way down because sometimes things happen and they get inputted and it'll mess up everything. So make sure that go all the way down. It goes past 9, so keep clicking down and make sure it's all clear. From here, let's type in our function. We have 1 minus e, so second divide, to the power of negative 0.25x. X and t mean the same thing. They're just a variable. That's what this means. X, t, theta, n, they just mean variables. All right, so we typed it in. Now we need to switch our window. So the reason why we need to switch our window, because there's certain things about probability. So I'm going to explain it right here. For your window, you hit the window button. You're going to be sent to here. It doesn't matter what it looks like right now. We're going to change it all. We need to change our x minimum to 0. The reason why, because time cannot be negative. X equals t in this example. So because of that, because in place of the x, there's a t, because of that, time can never be negative. You cannot go back in time. So because of that, we need to make sure it's 0. Time starts at 0, then it goes up. Then our maximum for x, our time maximum, is going to be 30. The reason why it's 30, because that was the max time that we calculated. When we calculated in part B, the max time was 30 minutes. Your scale should be 1. Your y scale should be 1. So if that's different, change it to 1. And then here, our minimum and maximum for y. So our y minimum should be 0. The reason why is because y in this case means percentage. When we solved for it, we got f equals 71 and f equals 99. That's the same thing as saying y equals 71 and y equals 99. And like I said before, you can never have something that is actually 100% or past 100%. So our minimum is 0 to 1. It's 1 because y1, that's the max. You can't go above 100%. 1 equals 100% and you can't go above it. 0.99 is 99%. So that's why all probability exists between 0 and 1. Probability is always a percentage, which is just a decimal, or it's a fraction. So this is our window. Now that we have our window done, we hit graph. And there's our graph. So do you notice our x's, it's 30 of them? And then our y's is only 1, 0 to 1. So you're just going to match the graph, 0 and 1 and 30. Just make sure it matches for your x's and your y's. All right, now we need to do part D. Part D says, what does f approach as t increases without bound in the positive direction? So forever, that just goes up and up and up and up and up, but it's never going to cross 1. As it goes x, aka t, time, as we just keep going in the positive infinite direction, so this way to the right, it's just going to forever approach 1. So as time passes, the probability that a car will arrive increases. The value of f approaches can be found by letting t approach infinity. And what value does it approach? It approaches 1. It will forever and ever approach 100%, but it will never cross 100% because we don't know that about a car. We don't know if a car will for sure come through the drive-thru or not. Part E, how much time must pass to have a 50% chance of a car going through the drive-through? So what we're looking for is how much time. Here, we're actually looking for t, and we can use our calculator. So what we're going to do is hit trace because we want to know where y is 50. So go hit trace and then use your left and right arrows to see that become 0.5-ish. You want to go around 0.5. So we scroll left. It's 0.96, 0.95, 0.94. All right, we're at 0.8. We're at 0.7, 0.6. There we go. Okay. So 0.49, 0.52. So it happens in between here. Now, it's happening, I say 2.5 to 2.8-ish. Your calculator sometimes gives you 2.7-ish to 2.9-ish. So it's happening between 2.7 and it's happening between 2.9. So when y is around 50, it's anywhere between around 2 to 2.8-ish. So we're going to round that up to 3 minutes. So after 3 minutes or 9:03 p.m., the probability of a car coming through the drive-through is 50%.